Hello everyone. Today we are going to talk about encrypted vMotion's architecture and performance, and also look at future directions for vMotion. I am Arun, software developer for vMotion, and I've been with VMware for 6 years. Along with me I have Shrikant, who is a performance expert of vMotion and has been with VMware for 10 years. We are going to be talking about some exciting new features which are currently under development, but we cannot promise you when those features will ship or part of which release they will be shipping. That's the reason for disclaimer. Let's look at today's agenda. Today's talk is divided into 3 sections. The first one is about encrypted vMotion, where I will cover the architecture and Shri is going to cover performance. The second section is about vMotion over 100 GBE, where I will again cover the architecture part and Shri will cover the performance. And finally we will talk about future directions for vMotion. Okay, let's get started. Let's look at how encrypted vMotion works, examine its architecture, and also look at the performance. First question, why do we need encrypted vMotion? So before we dive into the details, quick question for our audience. How many of you have used vMotion or configured a vMotion network? Please raise your hand. Okay, yeah. Okay, so all of you are familiar with vMotion network, right? So how does vMotion network of today look like? I mean prior to 6.5. When you take your VM and vMotion from one ESX host to another ESX host, we send the VMs, memory pages, device state, checkpoint, all of that over the vMotion network in plain text, right? So if you are an attacker and you have access to vMotion network, you can get all of the VM's data during vMotion. For this reason, we have always recommended our customers to keep vMotion network a separate isolated network. For example, nobody in your organization has access to the vMotion network, and it's also non-routable. So this has been the case from the time vMotion was introduced in 2003 until 6.5. Now what's been happening at this time in the industry? We've seen a lot of security breaches, right? The cost of security breaches is higher than the IT spending. So clearly we needed to come up with a better story, and to address customers' concerns, we came up with encrypted VMs. So the encrypted VMs are going to keep your VM's data encrypted while it's at rest. So when you power off the VM, your disk contents is encrypted. If somebody tries to read the disk or open any of the VM's files, all the data is going to be encrypted. But what happens when the VM is going to be vMotion, right? So we can't continue to have the old recommendation. So we came up with encrypted vMotion. So with encrypted vMotion and encrypted VMs, your VM's data is encrypted even when it's at rest or when it's in transfer during the network. Apart from encrypted VMs, encrypted vMotion can also be used for long distance. You have multiple data centers, you take your VMs from one data center and you vMotion it to another data center, you can use encrypted vMotion. And also the latest new feature, which is VMC, VMware Cloud on AWS. So you have your on-prem data center, you have your VMs, you can use encrypted vMotion to go to vSphere Cloud on AWS. So these are some of the reasons why encrypted vMotion is attractive. So let's look at how to encrypt vMotion. Right? So vMotion lives inside the kernel. Right? So we have to take VM's pages, device state, and transmit over the network. One of the choices we had was to use SSL. A lot of people would have been familiar with SSL, but the problem is SSL is in the user space, right? So what we have to do is take the VM's pages, send it to the user space, encrypt using SSL, again come back to kernel, transmit over the network. Clearly this has performance implications. So we cannot get line rate on 40 GB, 100 GB networks. So SSL is not a great option for vMotion because of performance. The next choice we had was using IPsec. So IPsec is IP security, it is in the IP layer, so we don't have to go to user space, we could just leverage IPsec. But IPsec is only supported on IPv6 and ESX. A lot of customers still use IPv4 for vMotion networks, so that's not going to be a complete story. And another problem is you need to configure every vMotion VM connect. For example, you can have your 64 hosts in a cluster. You have to log into each and every host, configure your vMotion VM connect to use IPsec. So that's another overhead. And another problem is you don't have per VM configuration. Some customers really like to choose a particular VM and then say, oh, I want to encrypt the vMotion of this VM because it's an encrypted VM. Encryption has a cost, so you don't want to encrypt all your VMs, so you might want to choose which VMs you encrypt. So with IPsec, we lose that flexibility in deciding which VMs to encrypt. So we also did not go with IPsec. So what we did is we took all these requirements and came up with our own encryption protocol for vMotion. So let's look at what this protocol is. First, we needed to have a crypto library in the kernel because vMotion lives in the kernel. So we took boring SSL and imported into our kernel, which is our VM kernel. This is FIPS certified, which is Federal Information Processing Standard. So now we have this kernel library. We chose to go with symmetric key encryption. The reason is you have two ESX hosts and your VM is going to go from one ESX host to another ESX host, and as long as these two ESX hosts share a key, we can encrypt. So symmetric key encryption is simpler compared to your public key, which involves certificate management, complex math. So we went ahead with symmetric key encryption. Now, what is our algorithm? We picked AES GCM, which stands for Advanced Encryption Standard, which is widely used in the industry, and Galice counter mode. So we picked AES GCM because it's again performance. In one go, you get both confidentiality and integrity for your message, where AES provides confidentiality and GCM provides integrity. So AES GCM is our algorithm, and AES GCM is compliant with NIST standards, which is National Institute of Standard and Technology. So that dictates 256-bit key. Our AES key is 256-bit. We have a 96-bit initialization vector and a 128-bit authentication tag. Shortly, we'll see how all of this is used to actually encrypt the message. So these are the four pillars of the vMotion encryption protocol that we designed. Okay, so let's look at how this works end to end, right? Let's take an example scenario. You have a vCenter server, you have a source ESX host where your VM is, and you want to go to a destination ESX host. So when you click your VM and then say you want to vMotion this VM, vCenter is going to generate a key for encryption, and it is going to send down to both the source and destination ESX host. And the key is generated and destroyed at the vMotion time. So there is no key management, the key is not preserved after the vMotion, so we just keep life simple. Generate the key, vMotion, throw the key away. Okay, so as we saw, this is symmetric key encryption. Confidentiality is provided by AES, integrity is GCM, and the important point here is authentication. So VC, your vCenter server, provides the authentication. So what this really means is there is really no key exchange between the two ESX hosts. VC only sends the encryption key to the ESX hosts that participate in vMotion. So if you have the key, then you are either the source or the destination of this vMotion. There is no key exchange. Both the ESX hosts form a TCP connection and then start sending encrypted messages. So VC provides the authentication. Okay. After this, we encrypt all the vMotion traffic. For example, your VM's pages, your VM's checkpoint information, your VM's disk contents, everything that goes over the network is encrypted, and you are able to do a per VM configuration, whether you want to opt in or not. Okay. Let's look at how this works, the per VM configuration. Right? So the first option is disable. For example, we already talked about encryption has a cost. Say you have a set of VMs and you really don't care about their security, or that's not important, then you can just choose disable, where the vMotions will not be encrypted. We'll continue to work like the old way, where we'll just send plain text over vMotion network. The next option is more interesting. It's called opportunistic, and that's the default option. So when you create a VM in 6.5, it'll be set as opportunistic. So what we mean by opportunistic? So at the time of vMotion, we will go and determine whether your source and destination ESX hosts are capable of encryption. If they are capable of encryption, it will be an encrypted vMotion. If one of the ESX hosts that participate in the vMotion is not capable, then it will be a regular vMotion, which is unencrypted. A lot of customers want the ability to freely vMotion their VMs in the data center, and a lot of times they have a mix of ESX versions. For example, if you have a 6.0 ESX and a 6.5 ESX, then we cannot do encrypted vMotion. So in that case, if you select opportunistic, it will be a regular vMotion. Anytime you vMotion between 6.5 and 6.5, it will be encrypted. So that's the flexibility you get with opportunistic. If you really want security, like I always want this vMotion to be encrypted, then you select required. When you select required, your VM will only be vMotion to an ESX host that is capable of encryption. So if you have a mix of 6.5 and 6.0 and you select required, you will only be limited to vMotion within the 6.5 hosts. Another important point to note here is, if you have an encrypted VM, your only option is required. Right? Because you encrypt the VM, we just enforce the policy that it will always be an encrypted vMotion. So these are the three choices you have on how to use encrypted vMotion. Okay, so now let's see what are the security guarantees provided by encrypted vMotion. Encrypted vMotion, as we saw, protects data in transit. So what this means is, if you have an attacker that is listening to your vMotion network, and if they are trying to eavesdrop, like they are trying to listen or snoop the vMotion traffic, all they are going to see is ciphertext. Everything is encrypted, they will not be able to make any sense of the traffic. If they are trying to replay any traffic, we have a replay attack counter, and we will drop those traffics. Like we will not use the traffic which is replayed. And finally, if they try to tamper, they are going to change a bit or a byte in your vMotion packet and then inject it in the network, we will be able to detect that. So the GCM, which is Galile's counter mode, provides us message integrity with which we can detect any tampering. So these are the security guarantees that are provided by encrypted vMotion. Okay, what encrypted vMotion doesn't protect, right? Say if you have a compromised ESX or VC, you have a much bigger problem, right? So the attackers can have access to your keys, or if your network between VC and ESX, which is SSL, is compromised, then again they can have access to the keys and they can decrypt all the information, right? So if the data at rest or at use is compromised, then encrypted vMotion is not going to help you. You have a much bigger problem basically. Finally, encrypted vMotion also doesn't protect against denial of service. So denial of service here means vMotion, right? So if there is an attacker who is going to modify a bit in the vMotion traffic, or if they are going to replay vMotion traffic, then we'll ultimately fail the vMotion because we don't want to commit the traffic to VM's data, right? So if the attacker is continuously going to do any of this modifying a byte or injecting a traffic, you will never be able to vMotion a VM. So that's the downside, right? So they can do denial of service, which is the best thing we can do today because we have to drop the traffic. We can't take the traffic in. So these are the guarantees that are given by encrypted vMotion. Okay, so let's see how the vMotion protocol is actually encrypted. Okay, so this is your encryption header. As we saw before, it has a 96-bit IV, 128-bit tag, and an 8-byte counter. So why do we have this 96-bit IV? For example, if two of the VM's pages contain the same content, if you encrypt them with the same key, you will get the same ciphertext. So somebody who is listening to vMotion network might be able to infer some information saying these two pages are same, can try to decrypt the key or do something like that. So to randomize encryption, we need an IV which is unique per message. Next is the authentication tag. So our protocol had GCM, which is Galile's counter mode, which helps in message integrity. So the authentication tag here is going to compute a message authentication code and append to every single message. So if somebody is going to tamper the message, change the contents or inject a new byte, we will be able to detect that with the authentication tag. Finally, we have a replay attack counter, which is monotonically increasing. So if we have seen a message previously and if somebody is going to replay that message, we will be able to detect that with the replay attack counter and drop that message. So now let's see how we use this encryption header and how the vMotion protocol actually looks like. So this is an example of a vMotion message, right? So you have a vMotion header and vMotion data. vMotion data is your VM's data, like its memory pages or its disk or checkpoint, and vMotion header tells you like what kind of data this is, right? vMotion message is a payload to your TCP header, and then there is IP header, right? So when we encrypt vMotion, this is how your encrypted message looks like. So your whole vMotion message is encrypted. There is an encryption header for the vMotion header, and then we have an encryption header for vMotion data. So now why do we have two encryption headers? We can take the whole vMotion message and we could encrypt it and have a single header, right? So why do we have multiple headers? The reason is parallelism, right? We deeply care about performance during vMotion, and we have multiple encryption headers. So let's see how a regular vMotion works first, and then let's compare that with the encrypted vMotion. A regular vMotion has two threads, which is a prepare thread whose job is to prepare the message, and then we have a transmit thread whose job is to put the message on the vMotion network. So as the transmit thread is transmitting the message on the network, the prepare thread is going to go and prepare the next message. So these two threads work closely with each other, and the result is we can get close to line rate on 40 GBE networks. Now if you're going to introduce encryption, encryption is costly from a CPU point of view, right? So how do we get line rate on 40 GBE, 100 GBE networks with encryption, right? So we designed the encryption protocol to exploit more parallelism. So what we did is, first we split the vMotion data into multiple segments, and we introduced a new thread for encryption. For example, the prepare thread now prepares a message, but it segments the message into smaller pieces so that we could encrypt the smaller pieces in parallel. And then we had a dedicated encryption thread whose only purpose is to encrypt messages. So as soon as the prepare thread prepares a message, the encryption thread is going to pick a segment and start encrypting the segment. So as the encryption thread encrypts a segment, we also have the transmit thread which is waiting for the whole message to be encrypted. Only then it can transmit. So while it is waiting, it can actually pick another segment and start encryption in parallel. So these two threads, right, the encryption thread and the transmit thread picks smaller segment, encrypts in parallel. Once the full message is encrypted, the transmit thread is going to put the message on the network. So this is how we leverage parallelism, and the result of all of this is we get line rate on 40 GBE networks, which is really important. So this is the reason we came up with our own protocol to exploit more parallelism. We cannot get this with IPsec or SSL, right? So with this protocol we get parallelism, we get line rate, and let's see how encrypted vMotion's performance compares with regular vMotion. So at this point I will hand over to Shri to talk about the performance of encrypted vMotion. Thank you.
Thanks, Arun. Let's now understand the performance implications of encrypting all your vMotion traffic. We have primarily three performance goals. Our very first goal is to make the migration as fast as possible. Our second primary goal is to make the migration as transparent as possible to the guest applications. Throughout the migration, we monitor the application level performance metrics like throughput, latency, And we also see how quickly the guest resumes to normal level of performance at the end of the migration. In fact, towards the end of the migration, there's a time where we need to quiesce the VM on the source host, take a checkpoint state, transfer this state across the vMotion network to the destination host, and then resume the VM from the checkpoint state. This entire phase is very critical to us because during this entire phase, the VM is not executing any instruction at all. So we particularly pay a lot of attention to this phase to make sure this entire phase is less than half a second. And as Arun mentioned, we also deeply care about efficiency, so we also pay a lot of attention to the CPU usage of vMotion. The testbed we had 2 identical Dell servers with latest Intel Broadwell processors, and you can see each of the hosts also had a 410GB NX. Encrypted vMotion requires that you use processors that support AES new instruction set. This is mainly for performance. AES stands for Advanced Encryption Standard. In our performance testing, we include several scenarios to emulate typical customer deployments as well as long-distance migrations. Our workloads also include a variety of workloads, including micro benchmarks and macro benchmarks like OLTP benchmarks, in-memory databases, and so on. For this set of tests, we are using Redis as a guest application. Many of you in the audience might be familiar with it. It's an in-memory key-value data store, and it's extremely popular in Docker world. The VM had 4 instances of Redis, each with a key space of 150 million keys. As you can see in this table, we had an idle VM scenario and also several active VM scenarios. In all these scenarios, you can see we are varying the mix of get and set operations. And the VM was really busy in all these scenarios. It was almost nearly 70% saturated. So let's quantify the performance impact of migrating this active VM, which is running a real-world application. In this graph, we're showing vMotion duration and vMotion switchover time with and without encryption. So let's take a look at the blue and green bars. The blue bar shows the vMotion duration without any encryption, and the green bar shows the duration when we turn on the encryption. And you can see that for all the test scenarios, the difference between the blue and green bars is pretty minimal. The line graphs which are plotted on the secondary y-axis, they show vMotion switchover time with and without encryption. These line graphs are more interesting because if you note, as we move along the x-axis, there's a slight increase, and it's pretty gradual. This increase in switchover time corresponds to the increase in set operations in the workload mix. It is expected because the get operation is a read-only operation, whereas a set operation modifies a memory page. When you have a write-heavy workloads, you should expect a slight increase in switchover time because of the need for us to send more dirty pages during the switchover time. This reflects in the slight increase in the switchover time. Just something to keep in mind. But more importantly, the impact of encryption on duration and switchover time is pretty minimal. So in this graph, we are looking to see what is the impact of encryption on the peak usage. So as you can see on x-axis, we varied the amount of network bandwidth from 10 GBE all the way to 40 GBE. And in each of these scenarios, we are seeing what is the line rate that vMotion can get with and without encryption. And you can see that in all the scenarios, even with encryption on, we are able to reach line rate. But as Arun mentioned, there's a CPU cost to that. Let's quantify the CPU cost of it. In this figure, I'm showing 2 graphs, which shows vMotion CPU usage with and without encryption on both source host and a destination host. The workload that I'm using is a memhog benchmark. It's a micro benchmark. It's extremely memory intensive. What it essentially does is it spawns few threads inside the guest application, inside the guest, and each of these threads linearly scan the entire guest memory and they just change a random byte in each memory page. And they do so in an infinite loop. So you can expect there's going to be a lot of dirty traffic. So we are capturing this CPU usage when the vMotion hits line rate. So let's understand this better. For instance, if you look at the 10 GB scenario, vMotion requires less than half a core without any encryption. But as soon as we turn on the encryption, to reach line rate, vMotion requires more than 1 core. Once again, on the source host, if you look at the topmost one, 40 GB scenario, you can see that without any encryption, vMotion requires a little over 2 cores. But as soon as we turn on the encryption, it requires nearly 6 cores. Similarly, on the destination, we have the data points. And when you look at all these data points, we see 2 interesting trends. The first is, as shown by the dotted line, vMotion in general requires more CPU on the destination than source. The second interesting observation is, even though vMotion requires less CPU on the source, the encryption overhead is much higher on the source than destination. This is because the encryption is much more compute intensive than decryption. But just as a summary, as a rule of thumb, remember that for every 10 GB of your vMotion traffic, you can expect little less than a core on the source host and little less than half a core on the destination to take care of all these encryption-related overheads. So let's take a quick look at some of the implications when you're doing a long-distance migration. Here is a logical layout of our testbed, where you can see we have 2 data centers, each hosting a unique vCenter server. And you can see that there's no shared storage across the sites. That means for our migrations, we are not only migrating the VM's memory, but we are migrating its disk as well. Here's the actual testbed that we used. It's pretty much the same as that we used earlier. The only difference is we are using a 1 GB network to simulate a more realistic bandwidth for long-distance migrations. And we are also using an appliance to inject latency into the vMotion network. The workload we are using is DVD store. It's an OLTP benchmark. So as you can imagine, it's the performance metric here is database server throughput, which is orders per second. In our test, we're using a SQL server running on a Windows VM. This figure here shows vMotion duration as we vary the latency from less than 1 millisecond all the way to 150 milliseconds. The graph looks pretty boring, with all the bars of same size, but that's the key point of it. What this graph is telling is, even if you vary the latency, vMotion duration is still a constant. In other words, thanks to all the latency-aware optimizations we added to the vMotion stack, whether you're doing your migration in your local data center with less than 1 millisecond round-trip latency, or whether you're doing a migration across the continent over a 150 millisecond wide area network, we offer you the same vMotion performance guarantees. What about the guest performance? Let's take a quick look at impact of encryption and long distance on vMotion performance. What we're looking here is SQL server throughput in orders per second before, during, and after long distance vMotion. As you can see here, we're using a 150 millisecond round-trip latency network. And prior to the start of the migration, you can see the data server throughput was about 225 orders per second. And throughout the migration, the impact is pretty minimal. The only noticeable dip you see is towards the end of the migration. That's when, as I said, we need to temporarily quash the VM on the source host and then quickly resume it on the destination. Once again, the impact on the guest is pretty minimal, even though we are migrating on a 150 millisecond round-trip network. So let's take a look at some of the performance numbers for vMotion. But before I show you some of the performance numbers, I want Arun to set up the stage to describe what the vMotion architecture is, and then we'll look at the performance numbers.
Okay, so let's talk about vMotion network and in general ESX network stack to understand how vMotion today works in terms of saturating your network cards. Let's look at the vMotion performance timeline. From the time we introduced vMotion in 2003, how did we change vMotion to take advantage of all the networking enhancements that have happened over the years? Right? So in 2003, vMotion was primarily designed to work with 1 GBE network. Right? Your VMs can saturate 1 GBE. Then later on, few years down the line, we got 10 GBE networks. So at that time, we moved away from our original design, which was more like a request response. We send a page, once the page is reached, we send the next page. So that's request response in 1.0. In 4.1, what we did was we moved to streams. So we take a group of pages and we have a dedicated thread for transmission of those pages, which we call vMotion stream, to get line rate on 10 GBE networks. So the next one was to introduce support for multiple NICs. So you can have multiple vMotion VMK NICs, each can have its own physical NICs, so you can have multiple 10 GBE cards, so that your VM can vMotion faster. Okay, so we've been talking about getting line rate, performance. So why is this really important? Why should the vMotion time be shorter? When the VM is being vMotion, as Shri showed you in the previous slide, that there was a slight impact on the guest performance during vMotion. So this is the reason that we want the vMotion time to be shorter, and if we want the vMotion time to be shorter, we have to take advantage of whatever the network that is provided to us. We should try to get line rate on the latest network cards. So that is the reason we've been constantly improving vMotion, so that we always get line rate. So a few years down the line, 40 GB NICs were introduced, and what we did was we introduced more parallelism in vMotion stream, which we saw a few slides ago, where we had two dedicated threads. One's purpose is to prepare the message, the other one is to put the message on the network. So with this architecture, we were able to get line rate, close to line rate on 40 GBE networks. Then in 6.5, we just saw that how encrypted vMotion works, right? So we extended our parallelism to 3 threads, where one is going to prepare, the other one is encrypting, while the last one is going to transmit, right? So by exploiting more parallelism in terms of using CPU cores, we are always able to get line rate on the latest and the greatest networks. Okay, so this is a brief summary of our performance timeline, right? So what is coming next? So the next one is 100 GBE. We are talking with our partners who are now having 100 GB cards out there, and we are looking at how can vMotion take advantage of 100 GB networks. So the time to vMotion your VM is going to be shorter, and the impact because of vMotion is going to be almost minimal on your VMs. Okay, before we get into the details on how we've designed our vMotion network for 100 GBE, let's look at how the ESX network stack is designed. vMotion stream architecture. So vMotion, as we saw, has a stream, and for encryption we have 3 threads: prepare, encrypt, and transmit. So this is a single vMotion stream. So how does this single vMotion stream map to your vMotion VM kernel NIC? So a single stream is created for one vMotion VM kernel NIC. So this vMotion VM kernel NIC has a software queue for dispatching your transmit or receive packets. So this vMotion stream, when it sends a packet on the network, will be queued to this software dispatch queue, right? So this is the software stack. And how does this map to your hardware? So you have your physical NIC, and then your physical NIC has your hardware transmit and receive queue. So your software queue will enqueue packets from the software queue into the hardware queue, which will actually be transmitted on the wire by your network card. So this is the high-level architecture of the ESX network stack that the vMotion uses today. And let's see how we can tune this to get close to line rate on 100 GBE and look at 100 GBE performance. So for this, I'll just hand it back to Sri, who will talk about how to tune this. Thank you.
Okay, let's take a look at some of the performance numbers. The current design that Arun talked about, it works really great when you have a 10 GB deployment. Even when you have a single VMK NIC or a single TCP stream, we can get line rate. You can see there's no bottlenecks anywhere at all across the entire stack. But in the new 100 GB deployment, this current design isn't quite adequate. Because when you have a single TCP stream, the vMotion stream helper, which does the bulk of vMotion processing, is completely CPU saturated. You really need a lot more stream helpers running on multiple cores to be able to scale the throughput on 100 GBE. Just adding more stream helpers doesn't do the trick, because the receive queue inside the PNIC becomes a bottleneck. This comes as a surprise to many, so let me explain. In ESX environment, all the NIC drivers use NetQ API or the NetQ specification to classify all the received traffic over different hardware queues inside the PNIC. And NetQ API uses layer 2 packet classifier, because using a MAC address of a VM or the MAC address of a VMK NIC is just a natural way for us to partition all the network traffic over different receive queues inside the PNIC. So even if you have multiple TCP streams on a given VMK NIC, they still end up getting processed by the same hardware queue inside PNIC, which becomes a bottleneck. An easy workaround here for you is you can create multiple VMK NICs on a single PNIC. For instance, in this example, we are creating 2 VMK NICs. Each has its own MAC address, so the NIC driver can easily load balance different TCP streams onto different queues, and you can get good scaling. So let's take a look at some of the performance numbers when we use this workaround. In this testbed, I'm using latest Dell servers with Broadwell processors, and each of the hosts has a 100 GB Mellanox NIC. And once again, I'm using an extremely memory-intensive memhog workload. And you can see on x-axis that I'm varying the number of VMK NICs, and I still have a same 100 GB PNIC. As you can see here, we can get very impressive scaling when you add more VMK NICs. We are almost hitting 80 gigabits per second with 6 VMK NICs. But once we turn on the encryption, we see there is some limits to the throughput, because, as I said, encryption is extremely CPU intensive. We're looking to address this issue in the future ESX releases by adding more encryption level threads. But more importantly, what we see here is you still need to create 6 VMK NICs today in 6.5 to get an impressive throughput on 100 GB, which is really not convenient, right? So let me walk through some of the optimizations we are working towards fixing this issue. Firstly, we are trying to leverage all the PNICs features, which is the receive side scaling that all the PNICs support. The idea of RSS is it's a standard network driver technology, which distributes all the packet processing onto different queues. By using RSS and more streams, we get some scalability, but not the full scalability that we want. As we keep adding more stream helpers, the bottleneck now shifts the dispatch queue at the VMK NIC level. As Arun mentioned before, currently we only support 1 dispatch queue per VMK NIC. It's because it's never been an issue before. But with 100 GB deployments, we are beginning to see that this is an issue. So we're going to fix this by adding more dispatch queues in the future ESX releases. We're also adding more changes to the PNIC driver level to give us more further gains. So, as I said, we are adding more software RX queues here. And let me explain, as I said, we're also making changes at the PNIC driver level. So let's review how RSS works today. For each incoming network packet, the NIC computes a hash value and uses it to index an indexion table and then assign a receive queue. This generally works quite well, but more often than not, what we've seen was the hash function used by the NICs sometimes don't yield very optimal values, because of which, even if we have a 7 or 8 vMotion streams, we end up using, let's say, very few queues as shown in this picture, which limits vMotion throughput. So we are working with our networking partners, including Mellanox, who is in the audience today, to implement dynamic RSS at the PNIC driver level. The idea is the NIC is going to expose the indirection table to the ESX. So that way ESX can implement load balancing logic for the RSS queues. Let's say if our ESX sees that one RSS queue is very heavily used, we can move some flows from this heavily used RSS queue to a lightly used RSS queue. That way we can leverage all the RX queues as well as all the PCPUs. In summary, we are adding optimizations across the entire stack, including vMotion, where our goal is to instantiate appropriate number of stream helpers, and inside the VM kernel network stack, where our goal is to create the appropriate number of dispatch queues, and inside the PNIC, where our goal is to leverage all the RX queues. And I'm happy to tell you that with all these optimizations, our prototypes are showing very impressive numbers. With a single VM NIC, we're almost able to get 85 gigabits per second. And we also have a demo where we'll show you, a single VM NIC is able to get such impressive throughput. But before I show you the demo, I just want to clarify two critical things when it comes to vMotion CPU usage and the network usage. Here, once again, we're using the same testbed that I talked about, and I'm using an extremely memory-intensive workload. This figure here shows vMotion's network usage under different scenarios. As you can see on y-axis, we used an idle VM, we used a VM with a single Redis instance, and so on. And in all these scenarios, the vMotion's peak network usage changes a lot. This is because vMotion network usage is highly dependent on the guest, how the guest accesses its memory and how it modifies its memory. vMotion network usage is also highly dependent on the phase of vMotion. Here I'm doing a dissection of the entire migration. In this particular case, I'm doing a vMotion without any shared storage. So I'm not only migrating the memory, I'm migrating its disk as well. When we do vMotion without shared storage, we always copy the disk first. During the disk copy, you always see slightly much lower throughput usage because most of the time we're always limited by the storage IO bandwidth, either on the source host or the destination host. But if you have a really expensive storage arrays on both, and if you don't have any bottlenecks at all, you will see that our transmit rate always starts at 2 gigabits per second, and we gradually increase the transmit rate just to avoid overwhelming the destination host. In our particular case where we had a NVMe storage, you can see that by the end of the disk copy, we almost hit 6 gigabits per second. After the disk copy, we start copying the memory. Most of you may be familiar with how vMotion memory copy works. We do it in an iterative fashion. Okay, in the first phase, which we call pre-copy 1, we copy the entire guest memory. During the subsequent phases, we only copy the memory pages which are modified during the previous iteration. So that's why we call it an iterative copy. During the first iteration, which we call pre-copy 1, we are seeing a pretty impressive throughput, but still we don't hit the line rate because this is the time we're also allocating memory on the destination host. So we are somewhat throttled by the memory allocation on the destination. But once we go to pre-copy 2 and beyond, there's really nothing stopping us. We can almost hit the line rate. So just something to keep in mind because when you see the vMotion throughput is not as good, you should also check which phase it is in. Now let's quickly see a short demo. It's just a 2-minute demo, but it will just touch upon all the points we just talked about. As you can see, we're going to do a vMotion over 100 GBE, and you see a VC here with just 2 ESX hosts, and host 1 and host 2. And a host 1, we have a single VMK NIC configured over a 100 GBE PNIC. Likewise, in the host 2 also we have a single VMK NIC which is going over a 100 GBE PNIC. On host 1, we have a Linux VM configured with 750 gigs of memory, and it's extremely active. Almost 400 gigs is pretty active. So we are opening 2 terminals here, one terminal to source host and the second one to destination host. Now let's start the migration. I'm using all the default options, and we're only doing compute vMotion. That means we are migrating from host 1 to host 2 with a shared storage. So you can see that relocate task just started. Now let's open two terminals, one to the source host, and here I'm going to track all the vMotion related messages in VM kernel log. You can see that we just started the migration with 8 streams. And on host 2, let's track monitor the network usage through ESX top. I'm going to the network screen here, and we see that we have a single VMK NIC and a single 100 GB NIC. And during the pre-copy, you're seeing a really impressive throughput, more than 40 gigabits per second. As I mentioned here, during this phase, we're also allocating memory on the destination. That's why we're somewhat limited in the throughput usage. Now we're almost nearing the end of the pre-copy. We just finished the pre-copy 1. And you can see the average pre-copy bandwidth there. Now, once we hit the pre-copy 2, we are seeing more than 75 gigabits per second. But as I said again, here we don't need to allocate memory because memory is already there. So we can, at this point, the only limitation is how much bandwidth you can give to vMotion. So we are almost finishing the end of the migration now. So we just finished the migration now. And if you go to the VC, you will see that if you choose that relocate task, you see that we just took little over 2 minutes to migrate this huge master-sized virtual machine. So now let me hand it over to Arun, who is going to talk about some of the exciting features which are coming for vMotion. Thank you.
Okay, so let's look at some future directions for vMotion. First one. All of you know and love vMotion, but how many of you know what Snowball is? AWS Snowball. Okay, so I'll give you a quick one-line definition of what Snowball is. So AWS has a service called Snowball, which you can use to copy your VMs which are running on-prem and then ship it to Amazon Web Services so that you can start your cloud there. Why do you need Snowball? For example, if you have like a 1 petabyte data center, like your VM size is 1 petabytes, sending all of them over network is going to be really expensive for you, right? So when you have these huge data centers that you want to move to AWS, you can actually use Snowball service to copy them, ship them, and then start them on AWS. Now, why are we working with AWS and Snowball? This is because of our vSphere cloud on AWS. A lot of customers are interested in moving their data centers, which they own, to vSphere on AWS. So by using Snowball, we just want to make our customers' life easier in moving to vSphere on AWS. So let's see how vMotion is going to work in combination with AWS Snowball. So in this case, let's say you have an on-prem data center which has ESX, vSAN, NSX, like the software-defined data center that everybody knows, and you want to move this to AWS, vSphere on AWS, right? So that's the scenario. So as a customer, you will just make an order for AWS Snowball, okay? So the Snowball will be shipped to your data center. You connect the Snowball to your software-defined data center, and then you transfer all your VM's contents. So the important difference on just using Snowball and then using Snowball plus vMotion is when you do the transfer here, the recommended workflow from AWS is that you power off your VMs. So you power off your VMs on your data center, then copy to Snowball, ship it to AWS. But with vSphere, you don't have to power off your VMs. You can continue running your VMs. What we're going to do is we'll take a snapshot of the disk and then copy the disk to Snowball device. But you can let your VMs run. While your VMs are running, we'll ship the Snowball, and then all the contents from Snowball will be transferred to S3, which is simple storage service from AWS. So the next step is from S3 we are going to pull all your data into your vSphere based cloud in AWS, right? So you create your own data center which again has vSAN, vSphere and NSX, and then we get all your disk contents into your vSAN data store. So once you have all of this set up, then what you could do is you can just simply do a cross VC vMotion. So what are you really getting with Snowball plus vMotion? The time to vMotion your VM reduces because we are seeding your vSphere on AWS with all the disk contents. So when you do vMotion and when you also move your disk contents, 90% of the vMotion time is spent in moving your disk. Only 10% of the time is spent in moving your memory. So when you use Snowball, we save that 90% of the time. So you can quickly vMotion your VMs to vSphere on AWS. And since you're using vSphere, you can run your VMs all the time when you're actually transmitting your data via Snowball. If you're just going with AWS, you have to power off, but you don't have to do that here. And it typically takes 10 days for your Snowball device to ship from on-prem to S3 to get it on AWS. With vSphere, you can keep your VMs running all those 10 days. And when you do vMotion, it's just your 1 second downtime, and then you can start running on AWS. So this is like really exciting and powerful, and a lot of customers who are interested in moving their data center to AWS are planning to use this Snowball service along with vMotion. So we're going to call this SnowMotion, and we can't promise you when this will ship, but we are working closely with AWS to make this happen and make life easier for our customers. So that is Snowball plus vMotion. So apart from that, we are also working on active passive storage replication. So we saw with SnowMotion that it takes 90% of your time to move your disks, right? So what if you have replication already? So if you have replication to your vSphere data center in AWS or your secondary data center, we just want to take advantage of your replica and not move your disks. That is strictly going to reduce the time to vMotion. So in vSphere 6.0, we added support for active-active replication. So active-active synchronous replication, active-active asynchronous replication already works today. So right now, we are working with active-passive replication vendors because a lot of customers have active-passive based storage replication. Active-active is more expensive and it's not found widely. So we are working to enable this active-passive replication so that you can take advantage. A lot of customers can take advantage of this and actually not move their disks during vMotion. An important point to note here is you need vVols, like virtual volumes, that's a type of storage, to actually take advantage of this feature. The reason we need vVols is a way to actually have per VM storage, right? When we are going to vMotion your VM to your secondary data center, we want to be able to reverse the replication direction for your VM. And this is currently possible only with vVols because vVols provide a per VM granularity. So if you vMotion a single VM, then we will only reverse the replication direction for that single VM. So this is not possible with VMFS because for storage vendors, the replication policy is at a LUN granularity, and with VMFS, you take a LUN, format it into VMFS data stores, and you can have hundreds of VMs. So when you vMotion a particular VM, we cannot reverse the replication direction for that single VM. We can only reverse replication direction at a LUN level. So that's why vVols are so interesting and required for this active passive storage replication support. Okay, so that is taking advantage of replication and not moving your disks. So apart from this, we are looking at next generation hardware, right? So there are a lot of new hardware enhancements. An interesting one is NVM. So this is the next generation of non-volatile memory. So Intel has recently come out with 3D X-Point, where they claim it's like the next generation flash, but its performance is close to memory. And the form factor is going to be your DIMMs. Like like your RAMs, you can actually buy these DIMMs and then insert into your servers, but you get persistent memory. So it's really fast. It's more in characteristics of memory in terms of its performance. So how do we migrate VMs which has this persistent memory? So we use the same technology that we use for moving VM's memory, which is iterative memory pre-copy, to move this persistent memory of your VMs. So if you buy one of these latest new servers that HP or Dell or anybody shipping, and you have your VMs which has this persistent memory, you can actually vMotion these VMs. So we support that. So the next point is RDMA over Ethernet. So this is a technology that is slowly becoming popular. As Shri mentioned, the cost of encryption is really high in terms of CPU. You need almost 1 core per 10 GBE. So if you have a 100 GBE network, you're looking almost like 10 cores of CPU to do your encrypted vMotion. That's really expensive, right? So what we're doing is, how can we reduce the cost of vMotioning VMs on 100 GBE? So we are looking at RDMA for that. So with RDMA, we offload all of the CPU expense to the RDMA card. So it's going to take over instead of your CPUs, and you can actually use your CPUs to run your VMs. So that's why RDMA over Ethernet is interesting. When we talk to a lot of customers, they don't want to do InfiniBand for RDMA, right? So InfiniBand is like, that's really expensive. You just don't want InfiniBand only for the purpose of vMotion. So RDMA over Ethernet is really exciting to us because the customers can continue using their Ethernet network, but just buy these new RDMA cards, which are like not so expensive. Okay, so the next one is PML, which is called page modification logging. So this is a feature in the latest new Intel and AMD CPUs. For vMotion, we need to copy the VM's memory. For that, we need to trace the VM's memory. We need to know when a VM writes to its page. So this is all done in software today. So that's why you see the overhead when you vMotion a VM. But the next generation processors actually support tracing these pages in hardware. So it's like hardware assisted virtualization. So the cost of a vMotion from a guest perspective really goes down when we start using these next generation hardware features such as page modification logging. We no longer have to trace the VM's pages in software. And finally, 4KN disks. A lot of disk vendors are now looking at capacities beyond 6 terabytes. So they want to go to larger and larger capacities. So your 512 byte sectors do not allow that. So there is a lot of overhead. So what they do is they use the 4KN technology right now, which has less overhead for your disks. And what do we do with this is, how do we move the VM's disks when the VM actually uses 4KN native? So we are going to rewrite some of our vMotion code to support VMs which use both the 512 byte sectors and 4KN sectors, so that you can natively vMotion these VMs. So these are some of the technologies that are currently under development, and we can't promise you when it will ship, but at some point we hope to deliver these so that you can take advantage of your latest new hardware when you buy them. Okay, so that brings us to the end of the presentation. Let's do a quick recap of what all we looked today. First one is, vMotion is continuously looking at the latest new technologies, customer feedback, and constantly improving. For example, encrypted vMotion, all your traffic is encrypted. You can go from one data center to another data center. You can securely vMotion. At the same time, we maintain the performance that all of you know about vMotion. So encrypted vMotion is as good as your regular vMotion in terms of the total vMotion time, in terms of vMotion bandwidth, in terms of your VM application downtime of 1 second. It maintains the same guarantees as your regular vMotion. And we also demonstrated that with monster VM migrations, you are able to achieve close to the line rate on 100 GB networks. So we just saw it took 2 minutes to move a 750 GB VM. And finally, what's next is we are helping our customers to adopt public cloud by working closely with AWS. vMotion is going to interop with Snowball, which is an AWS service, to quickly onboard customers to vSphere on AWS. Again, we're going to support active passive replication. If you use your AWS data center as your secondary data center to replicate all of your VM's content, then we can quickly vMotion your VMs there by leveraging replication. And finally, we saw that we are working to address all the new latest hardware advancements. So that's the quick summary. And we also have a lot of other extreme performance sessions that you can go and attend. Here is a quick list of all of them. We also have extreme performance labs where you can actually go and try the latest new performance enhancements in 6.5 and also all the performance challenges in the labs. There is a survey which you can take to actually let us know what your expectations are for the performance sessions. And this is the survey for this particular session, like what is your feedback and how do you want these sessions to be organized going forward. And we can take questions right now if you have anything on Encrypted vMotion. And thank you for coming and attending these sessions. The floor is open for questions.
Okay. My first question is on the packet for the counter. Is it encrypted, the counters, for the replay counter? Sorry, thank you.
No, the encryption header is not encrypted. So the counter is still plain text.
Okay, so if a hacker were to able to not replay it, they could still capture it and just change the counter though, couldn't they, and dump it back in?
Yeah, so if they change the counter, we will actually get another packet with the same counter. At that time, we will fail the vMotion.
Okay, but what if the counter, they modify it and they change the counter on the packet?
So,
and it's a unique one that hasn't been seen before. But it's replaying the same actual data. I know it's complex, but
right. Yeah.
Still,
so that's a good point. So if they modify it, we will not be able to detect it, but they have to make sure they modify all the rest of the packets.
Of course.
If they fail to do any of that, then we'll detect and fail the vMotion. But if they listen to every single packet and they modify each one of that, then we will not be able to detect it. It's plain text.
So that's my first question. My next question is, are you guys in the future by chance going to make it where the customer can spin up more threads? They can choose to configure it themselves. So we say, hey, we have overhead CPU. Why don't we go ahead and add more threads so that we can, get our vMotions around?
Yeah, you can do that today. You can.
No, not the encryption level threads and all, right? I mean, we
okay.
plan to support, but they will be all coming under advanced settings. Our goal is to make it all transparently work, right? I mean, you just do it and we will see how much bandwidth you have, how much workload you have and so on, how much CPU you have. That's our goal. But for people like you who want to, think around more, we will give some advanced option through VSI interface or something.
Great.
But we won't be exposing to all the customers.
Makes sense.
Yeah.
Makes sense.
So we do have an option today where you can go and decide how many stream threads you want for your 100 GB card, right?
Sure.
But it doesn't say how many threads for encryption or transmission. It just says
that's
total
okay.
stream
At least you're getting some more options.
Yeah.
That's great.
Yeah.
My next question is about the Snowball tech you guys are looking at. So I work for a bank. Banks don't do cloud. I apologize. We have our own private cloud. Okay. My big question is, in regards to I ship VMs around all the time to other countries. I would love to have it where I could just toss a VM on a hard drive, bring it up at another site, and do the same thing that you're doing with AWS. Is that the same goal?
Yeah.
Without AWS as well?
Right. So initially we are working with AWS. At some point, we definitely have a roadmap item to support private clouds. We have two different data centers, and we understand that you want to go between both of them. And once we have the story finished for AWS. We are going to take that and then see how we can backfill Snowball.
Sounds great.
Yeah.
Thank you very much.
Yeah. Thank you.
Thank you.
Any more questions?
Yeah, back on a slide, I think it was 17 or 18, you guys were showing your test bed, and you had different variations of get sets. And the line actually crossed a couple times where it looked like it was faster under encryption.
What we're just showing you is there's always an inherent noise in the test, right? It's always less than 5%. We typically don't care, But there's always some noise, because when you run some tests, you get, let's say, 100 G, or some throughput, When you run exactly the same test, you may not necessarily get that.
Maybe it's 15 or 16, but
I think
right here. So I just wanted to, that's why I wanted to make sure. Was it just some variation?
Yeah, it's just some variation.
Okay.
What we're just telling is whether you turn on encryption or not, the impact is pretty much the same. You don't need to worry. The only cost you're paying is in terms of the CPU cost. And we're trying to see how we can address it through use of RDMA or other technologies. But right now, you get the same performance as you're used to in terms of switchover time and guest performance. Everything will be the same. But just that you'll be using more CPU.
Yeah. Okay, great guys. Thanks. I enjoyed this.
Okay, thanks.
Thank you.